Hey everyone, welcome back to the channel. Now, if you've been following my recent videos, you'll probably know that I've been diving deep into the world of bioprinting. In our last video, we covered the key components of Bioink, which were cells, hydrogels, and the growth factor. Well, in today's video, we're going to take a step further and explore the actual processes involved in bioprinting. Now, how these bioinks come together in order to create functional tissue structures. If you're excited to see how science is pushing the boundaries of medicine, do keep watching. Okay. So as we have established in our previous video, bioprinting is defined as a layer-by-layer additive manufacturing process, and it's one that's very similar to the traditional 3D printing techniques that we use. But instead of using materials like, for instance, plastic or even metal, we go with the alternative of bioink in order to create these living tissue structures. Now, the entire bioprinting process can be broken down to three main stages. This is the pre-processing stage, the processing stage, and the post-processing stage. Okay, let's start with pre-processing. Now, the pre-processing phase is all about planning and preparation and designing everything, creating essentially what is a blueprint for the tissues that we want to print. Now, it begins with an extraction from a biopsy of a tissue to provide a biological model that should be recreated through bioprinting. Let's just note down extraction right here. Now, after this stage, we design and create what is a digital file for the bioprinter to read. Now, the files used here are mostly based on the CT and MRI scans. And the images collected and also compiled in this digital file are tomographically restructured to form 3D images. After that, the cells required for the process are selected and multiplied in order to form bioink. For this stage, we kind of need info gathered about the cells, so we kind of refer back to the biopsy stage. So to kind of sum up everything, we've come up with two things in the pre-processing stage. This is A, the design of the tissue or the organ, and B, the bioink. Now in the processing stage, this is the actual bioprinting stage. The bioink is placed in the printer in order to form a 3D structure. Now the bioink is placed onto the printer cartridge to be more specific, which is right here. And then it deposits the material based on the digital model that we've prepared in the pre-processing stage. Now, the printer right here kind of looks like an inkjet bioprinter. Oopsies. What this means, I'll explain later on. Okay. The diagram here looks like an external view of the bioprinting system, and diagram B here is a close-up of the print head and the cartridge system. Now, depending on the types of cells, the tissue complexity, the resolution required, and the type of structure, different bioprinting techniques are used. Now, there's several types of bioprinting techniques, but we have four common methods. These are inkjet bioprinting, extrusion-based bioprinting, laser-assisted bioprinting, and stereolithography. Okay. First is the inkjet bioprinting. This is also termed as the drop-on-demand technique. Inkjet bioprinting essentially deposits small droplets of bioink in order to build tissues layer by layer. It's commonly used for both non-biological and biological purposes. Now, the way that the inkjet-based bioprinting works is by ejecting liquid droplets using thermal or acoustic forces, illustrated right here. Okay. For thermal inkjet bioprinting, it electrically heats the print nozzle in order to generate pressure for the droplets. As we can see, the heater right here heats the print nozzle in order to generate a sort of pressure, I'd say, in order to drop these droplets. On the other hand, the acoustic inkjet bioprinting uses piezoelectric crystals in order to create an acoustic wave that breaks the liquid into droplets. Now, to be more specific, and in order to make this pertain to the diagram here, the piezoelectric actuator right here, it leverages the piezoelectric crystals in order to produce acoustic waves through the reverse piezoelectric effect. Yep. So inkjet printing is ideal for three things mainly. A, for low viscosity bioinks. This is because they're easier to print in droplet form. And also high-speed bioprinting. I think in inkjet bioprinting, droplets are dispensed rapidly, where thousands are fibered, I think, in a few seconds, allowing for quick tissue regeneration. And also cell viability. Now, compared to other bioprinting techniques, this inkjet method is a relatively gentle process, and it doesn't really involve a lot of stress on the cells. But this method isn't exactly the best for producing high resolution and also on printing complex structures. Now, this is because the droplet size itself limits the degree of precision. Now, examples for the inkjet-based bioprinting includes the regeneration of functional skin and cartilage tissues, where high printing speed allows for direct deposition of the cells onto the cartilage and skin lesions. Okay, next is extrusion-based bioprinting. Extrusion-based bioprinting is the most common method of printing for non-biological 3D structures. Now, in extrusion-based 3D bioprinting, there are mainly two techniques used. This is mechanical extrusion and fused deposition modeling, also shortly called as the FDM. Now, the mechanical extrusion is a process where materials are forced through a nozzle in order to create specific shapes, and it's used widely in both manufacturing and bioprinting. There are three primary methods under this. We have pneumatic extrusion, which is essentially compressing air in order to push low viscosity materials. And also piston-driven extrusion, where the piston or the plunger provides direct mechanical force, offering for precise control for medium or high velocity materials. And then finally, we have the screw-based extrusion approach. This is ideal for high viscosity bioinks, as a rotating screw applies consistent pressure. Now, each of the methods serve different applications depending on the material's properties and desired outcomes, and specifically the viscosities of the materials. Now, the FDM-based bioprinting, on the other hand, involves melting thermoplastic filaments at high temperatures and extruding them through a nozzle in the same layer-by-layer process in order to build a 3D construct. Now, both techniques rely on two key components. This is A, an extrusion system, and B, a positioning system, and they must work together with precision in order to create geometrically accurate structures. Now, extrusion-based bioprinting is particularly useful for printing high-viscosity bioinks, which allow for more stable structures, like, for instance, the cartilage or even bone scaffolds. Because it provides greater control over the deposition of large amounts of bioink, it is more suitable for printing larger tissue constructs. Alright, that is it for today, and in our next video we will be looking at the other two bioprinting methods and the final stage of bioprinting, the post-processing stage. Thank you.